Hello, good afternoon, everyone. Okay, we'll start the session now. So, I hope you can hear me. So, this is the NPTEL course problem solving session. So, we are into week 8. So, by now, I hope everyone is clear about what course we are doing and what are all the things we have covered till now. So, this course is Fluidization Engineering. The course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. And these live sessions are handled by myself, Ankar Kartika. I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, I would like to have any feedback if hear any feedback if you have. You can just put it in the chat box. I can read it at the end. Um, yeah, if not, we have been having these sessions every Saturday, 3 p.m. to 5 p.m. So, I hope these sessions are helpful as well. Now, let us start with the session. So the course layout is as follows. So it is a 12 weeks course, and in first few weeks, that is week 1 and 2, mostly we have seen the introduction to fluidization and what are the advantages and disadvantages of fluidized beds and industrial applications. So what exactly is fluidization? Fluidization is the process in which we pass a fluid at a sufficiently high velocity inside the packed bed so that the particle starts behaving like a fluid. So why do we need to go with such high velocities when we already know that if we are using it as a fluidized bed, the pumping cost, everything will be increased. So why do we have to go with fluidized beds? Because the contact area is enhanced. The contact between solids and the fluid is enhanced in fluidized beds. Thus, it is very convenient in cases of such things when we require. For example, like if we want higher contact between the fluid and the particles, we can go with fluidized beds. So in those cases, the mass transfer and the heat transfer coefficients are increased. So that is fluidized bed. And right now we have uh, advantages as well as disadvantages associated with the fluidized beds. What are all the advantages we have seen? What would be the disadvantage? Disadvantage is that when we use fluidized bed, chances of the particles escaping from the bed is quite high, which you might have seen already. uh, just a minute, guys, my Wi-Fi is gone. Okay, I am just connecting from, yeah, I connected from my mobile data. So yeah, if there is any network issue, please stay online. I'll be joining back in few minutes. So that is what I wanted to say. And coming back, what are all the disadvantages of fluidized beds? We have certain disadvantages like when we use fluidized beds, the chances of particles escaping the bed is quite high when we use the velocities at a very high level. And also, like particles may collide against each other, and because of that, the particles might also get broken and for this particular reason, if we are using costly materials, okay, just a minute, I'll be coming back. So, okay, I hope you can hear now. Hello? Yeah, I hope you can hear now. So coming back to the things, there was some power cut issue over here, and that is why it is happening. So coming back, what are all the disadvantages we have seen? Like when the particles might get eroded and broken off, and because of this particular reason, we cannot use valuable materials in the fluidized beds. If we want to have a quality if we want to maintain the particles, chances of using fluidized beds would be limited. In cases like the particles might get damaged in the sense that these particles, because of the rubbing against each other, they may chip off like after a prolonged use. So it has advantages and disadvantages as well, and but it is widely used in various industries like um, FC catalysis, separation, like various unit processes and unit operations use these, like catalytic reactions, all those things use fluidized beds sometimes when reaction is taking places, and also like drying and coating, those things also use fluidized beds. So this is just to give you an idea, and later we saw about the classification of solids. It is nothing but based on the solids density and size, we are classifying the solids into four classes. This is known as Gelda classification, which he did in according to the relative difference between the fluid and the particle density and the particle size. So the smallest size particle comes under the Geldat C classification, and comparatively larger ones like comes under Geldat A, and further larger ones like sand size particles comes under Geldat B, and the largest one comes under Geldat D. So Geldat C, since they are very small, cohesive forces play a very important role in these type of particles, and it is very difficult to fluidize such particles. Whereas in GelDat D, a larger bubbles tend to form, and we use spouted fluidized beds for that purposes. And like in between, A is FCC catalyst comes under GelDat A classification, and B, it is forming bubbles but not to up to the size of GelDat D. So these are the classification of solids, and in week 4 and 5 it is about flow pattern inside fluidization, wherein with different velocities we get different uh, like different regimes of fluidization. For example, but at low velocity, uh, at minimum fluidization velocity, we call it as incipient fluidization also. It is nothing but when the velocity of the gas or of the fluid which we are passing at that condition, the particle weight is completely balanced in the bed. These particles are loosely suspended, but it is not moving. But it is not tightly packed as in the packed bed condition also. So this is known as incipient fluidization or minimum fluidization. Till we are attaining minimum fluidization, up to with increase in velocity, the pressure drop inside the bed increases. But after minimum fluidization velocity, the pressure drop remains a constant. That is how we know we have reached the fluidized bed state. So at this constant condition, we call it different regimes we see. For example, in liquids we see homogeneous fluidization or particulate fluidization, and later we call, like if we are using gas, we can see bubbling fluidized beds, and if the bubbles are increasing in size, we call slugging fluidized beds, and further increase in the velocity, these bubbles grow in size and they almost burst, and the solid recirculation happens, and we can see regimes like turbulent fluidized beds, pneumatic fluidized beds, everything. So these are the flow pattern transition and frictional pressure drop. There are various equations available to calculate the pressure drop inside the bed, because it is one of the important factors when we are dealing with fluidized beds. Why it is an important factor? Because pressure drop only allows us to determine how to scale up the process in industries, and would it be economical or economically feasible to use those processes in industries. So that is what we have seen in week 4 to 5. And lastly, in week 6, it is about gas distributors. Gas distributors, again, it is an important factor. Why? In gas distributors, we place it at the bottom of the bed, above which we place the solids. So depending on the distribution type, a distributor type, we have porous plate distributor, perforated plate distributor, tube type, and bubble cap type. So in a laboratory scale and in industrial scale, we have different type of gas distributors, because in laboratory scale we can use whatever we want, but in industrial scale, if you are talking about at that high level, the main problem would be pressure drop, because it should be under our control, and also it should be economically feasible to use that at industrial scale. So that is a major influencing factor when we are talking about scaling. And so based on that, we have different type of distributors, and it should be producing uniform gas distribution also, and the flow pattern should be what we require. So this is gas distributors. And lastly, the important thing about fluidized beds and the important regime is the bubbling fluidized beds, which we always deal with when we are talking about gas solid fluidized beds. So when we use gas, the chances of bubble formation is quite high, and we need to have a complete understanding of bubbles in fluidized beds, because only then we can understand the mass transfer and the heat transfer phenomena if we are talking about that. So because these bubbles also act as a phase and influence the hydrodynamics of the bed in a very high level. So that is one thing. And in week 8, it would be entrainment and elucidation from fluidized beds, wherein the solids are being carried out of the bed by the incoming fluid. So we need to have the bed design in such a way that the solids are not carried out of the bed, and also like this loss is minimized. Later we can see about the attrition mechanism, wherein it is what I said about the particles getting broken down because of the continuous contact with each other. And later we deal with mass transfer phenomena and heat transfer phenomena happening inside the bed. And books and references, we have seen this multiple times, but the first one is Kuni and Levenspil's Fluidization Engineering. So I would suggest all of you to read this book for complete understanding of things happening inside the bed, because it gives you the idea of what is happening. If you want to take a career out of fluidized beds, or you are applying for a job and you are thinking of leveling up your skills, uh, like fluidized bed is very much used in industries, and you having a complete understanding of the fluidized beds is very good advantage which you will be having. So you, like why go have a shallow knowledge? So this book has a very in-depth understanding of fluidized beds. So at least one reading of it would be helpful for you guys. And second one is Gidaspo's Multiphase Flow and Fluidization. And this is again a very good book wherein it would give you an idea about the modeling aspects of fluidization also. And last is, third one is Gibbler's fluidization dynamics. And last is S.K. Majumdar's hydrodynamics and transport processes of inverse bubbly flow. So again, this is the book by Professor. So you can read. And yeah, now we can see about, so right now we are in week 8. So what we are going to do is we are going to solve 20 problems from week 8 assignments, and later 20 problems from week 7 assignment answers. So yeah. So yeah, we'll see. So we'll start with question 1 for, we'll start with week 8 problems. These 20 problems from week 8 are helpful in a way that it will be a guide for you to submit your assignment problems for this week. So this week's submission, I guess, is Wednesday. So please look into it and solve the problems related to week 8 questions, which for answer for which we can discuss in the next class. So now let us go into question 1. According to Davidson model, when the bulk density is similar to that of a particulate phase in the fluidized bed, then the particulate phase is dash. So this question is about Davidson model. Davidson model, do you guys remember what it was dealing with? It was dealing with bubble dynamics, right? So like they are one of the pioneers in studying the bubbles inside the fluidized beds. So, Davidson model, according to that, when the bulk density is similar to that of a particulate phase in a fluidized bed, then the particulate phase is dash. Option A, incompressible fluid. Option B, compressible fluid. Option C, viscous fluid. Option D, all of these. So the answer is incompressible fluid is the right answer, because what Davidson model was suggesting is that when bulk density is similar to that of a particular phase in a fluidized bed, then the particular phase is incompressible fluid. So as the bubbles rise, particles move aside as would an incompressible inviscid fluid of bulk density rho s into 1 minus epsilon mf. So what what their model is saying is that when the bubbles rise in the fluidized bed, the particles are moving aside, and the particles moving aside in such a way that how an incompressible inviscid fluid would do, the particles are moving aside in that way. So like they compared actually bubbles in fluidized beds and bubbles to an what how bubbles from arise from a liquid. So the comparison is made in that way. So because of that, these particles are moving aside when these bubbles are rising. So how are they moving? According to them, they are moving aside in such a way that how an incompressible inviscid fluid would do, and that incompressible inviscid fluid uh, would do, and because of that, these particles are also moving in such a fashion. That is what is he's doing. So it is incompressible fluid. So that is the answer. And the next question, so answer is option A is the right answer, incompressible fluid. As a bubble rises, particle moves aside, as would an incompressible inviscid fluid of bulk density. So this is what is stated in their postulate 2. If you go and read it, you will be able to understand it. And now let us move to question 2. And I would like to add that if you have any concerns at any point, I would ask you to stop me, and we can discuss at that point also, or else we'll have 5 minutes time at the end of the session. We can discuss at that time also. I hope it is clear. Now question 2, let us see. And if you want me to discuss it in any other different fashion that would be useful, that you feel would be useful, we can do it that way as well, because I want to improve my teaching also, like when I'm doing it. So your feedback and your suggestion would be helpful, because at the end, you people are what are the target audience. So like feel free to say any feedbacks or suggestions. Always the criticism is welcome. So now let us go to question 2. In question 2, according to Davidson model for gas flow at bubbles, option A, pressure distribution is unaffected by the motion of particles. Pressure distribution through the bubble is constant. The particulate phase behaves as an inviscid fluid. All of these. So answer is option D, all of these. So because according to Davidson model, what they said is that pressure throughout the bubble is constant. Also the particulate phase behaves as an inviscid fluid, that we have seen in the second postulate from the last problem also. And also pressure distribution is unaffected by the motion of the particles. So I'll just read out the Davidson model postulates. So the first one is bubble is solid free and it is circular in shape and mostly in two dimensional, and if it is they are in three dimensional they are spherical, and in two dimensional they are cylindrical. And as these bubbles arise, particles move aside as would an incompressible inviscid fluid of bulk density rho s into 1 minus epsilon mf. And also the gas flows in emulsion phase as an incompressible viscous fluid, and the pressure in lower part of bubble is lower than the surrounding bed, whereas at the upper part it is higher. Gas flows into the bubble from the below and leaves at the top. Why? Because at the lower part of the bubble it is lower than the surroundings, and at the upper part it is higher. So that is what is given in their postulates. So according to that, the pressure distribution is constant throughout the bubble. So option B is right. Pressure distribution is unaffected by the motion of the particles. So again option A is right. And in option C, the particle phase behaves as an inviscid fluid, and again that one is right as well. So answer is option D. That is, all of these are the right answers. So now Davidson model. A gas bubble is solid free and circular in shape. As the bubble rises, particles move aside as would an incompressible inviscid fluid of bulk density. Gas flows in an emulsion phase as an incompressible viscous fluid. Far from the bubble, undisturbed pressure gradient exists. So far from the bubble, undisturbed pressure gradient exists. The pressure in the bubble is constant. So these are the things given and everything is right. So now let us go to question 3. In question 3 it is asked that the fluidized bed regime is said to be fast bubble regime when dash, where UB, UMF and epsilon MF are bubble velocity, minimum fluidization velocity and minimum void fraction. So we generally say as slow bubble regime or fast bubble regime. So before looking at the options, I want to see what are slow bubbles, what are fast bubbles. So what are slow bubbles? The name itself suggests that the bubble moves slowly. So the bubble moving slowly, the emulsion phase or the gas phase surrounding it is moving comparatively faster. So remember, slow bubble regime. So the bubbles are moving slowly and the gas phase is moving faster. So because of that reason, the gas is can pass through the bubbles also. So that is what we call it as slow bubble regime. So because these gas are passing from the passing through the bubbles, we call it as cloudless bubbles also for the slow bubble regime. But what happens in the fast bubble regime? The bubbles are moving faster than the surrounding fluid, and gas leaving is slower. So what happens is that the gas leaving at the top is swept around and returns to bubble base. So consider this is the bubbles moving. If UBR, bubble rise velocity, and UMF divided by epsilon MF. So this is the fluid velocity. If UBR is higher, what happens? These bubbles are moving faster and the surrounding fluid is moving slower. So because of that, the circulation would be happening. Whereas this is in fast bubble regime. Whereas in case of slow bubble regime, what happens? This one is slower, this one is faster. So they just move through the bubbles. So there is no clouds in fast and slow bubbles, slow cloudless bubbles and fast clouded bubbles. So what is the question about? We'll see. In a slow fluidized bed is said to be fast bubble regime. So now can you say what is fast bubble regime? Fast bubble regime is nothing but where the bubble is rising faster. So the term slow and fast refers to the bubble speed. So here the bubbles are rising faster than the surrounding gas medium or the fluid medium. So dash what happens, what is the condition? So option A, ub is greater than umf by epsilon mf. Option B, ub is less than umf by epsilon mf. Option C, ub is equal to umf by epsilon mf. And option D, ub is equal to umf by epsilon mf. So now we know that ub is greater than umf by epsilon mf. Why? Because this is a fast bubble regime. So what happens when the question is asked about slow bubble regime? If the question is about slow bubble regime, UB is smaller than UMF by epsilon MF. Always remember the fast and slow refers to the bubble speed. So in fast bubble regime, what is the case? So option A is the right answer. UB is greater than UMF by epsilon MF is the right answer. Option A is the right answer. I hope it is clear to you. Now we will go to question 4. The fluid leaves the roof of the bubbles and recirculate back to the base of the bubbles in dash. Option A, slow bubble regime. Option B, fast bubbles regime. Option C, both A and B. Option D, all of these. Option B, fast bubble regime is the right answer, because we have seen that the fluid is leaving from the roof of the bubble and it is recirculating back to the base of the bubble. So that is what we call it as clouded bubbles in fast bubble regime. Why this is happening? Because the bubbles are rising faster than the surrounding fluid. The gas leaving the at the top is swept back and recirculated back to the bubble base. Region around the bubble penetrated by the circulating gas is called as cloud. So that is clouded bubbles, and we call it as fast bubble regime. In slow bubbles, these emulsion gas is rising faster than the bubbles. So it uses the bubbles as a convenient shortcut on its way through. It is not it is not moving around, but rather it is moving through the bubble. It is using the bubble as a convenient shortcut way in slow bubbles. So I hope you are now very clear with the distinction between the fast bubble and the slow bubble. Coming back to the question, the fluid leaves the roof of the bubbles and recirculate back to the base of the bubble in option A, slow bubble regime, option B, fast bubble regime. So option B, fast bubble regime is the right answer. I hope you are clear with that. Now we'll go to question 5. Okay, before that, question 4 itself we have if UBR is equal to 0, we have a stationary bubble, bubble is not moving, and UBR is equal to 0.6 times UF, that is less than UF. So we have slow bubble regime. As you can see, the gas is passing the bubbles, and if UBR is equal to UF, that is UBR is equal to UBR by UF is equal to 1, we have an infinite circle of cloud. The cloud is infinite in thickness at this particular condition, whereas after this the cloud thins with increasing bubble velocity. Here we can see that UBR is equal to 1.1 times UF. So UBR is greater than UF and UBR is very much greater than UF in these cases. So the cloud is thinning from with high velocity, but these are known as fast bubbles. This is slow bubble. So I hope it is clear. So this is the reference book. I have taken the image from Kuni and Levenspil's book. Now we'll go to question 5. In question 5, at what particular condition the gas does not mix with the recirculating gas? Option A, when gas leaving the top of the bubbles. Option B, when fast bubbles moves across cloud. Option C, slow bubble moves through the cloud, and all of these. So what happens in by now we are clear with concept of slow bubble and fast bubble, right? In slow bubble, bubbles rise velocity is lower than the emulsion gas speed. So the emulsion gas rises faster than the bubbles and uses the bubble as a convenient path on its way through the bed. So annular ring of gas circulate within the bubble. But in clouded bubble, when the gas leaving at the top is swept around and returns to the bubble base, we call it as a clouded bubble or fast bubble. Around bubble penetrated by the circulating gas is what we call the cloud. But what happens is that the rest of the gas in the bed does not mix with the recirculating gas. Are you clear now? Rest of the gas in the bed does not mix with the recirculating gas in the fast bubble regime. So the rest of the gas in the bed does not mix with the recirculating gas, but they move aside as the fast bubble with its cloud passes by. So there is no mixing of the recirculating gas and the rest of the gas in the bed. This is what happens in the fast bubble regime. So now I think you're clear. You are able to understand the distinction I am speaking about. In slow bubbles, the annular ring of gas in the circulates through the bubble and circulates within the bubble. But in fast bubble, what happens is that there is a recirculation of gas from the from the bubble top to the bubble base. This is known as cloud. But the rest of the gas in the bed, apart from the one in the cloud, does not mix with this recirculating gas inside the cloud, because these bubbles moves faster aside. Because the gas moves faster aside as the fast bubble with its cloud passes by. So there is no recirculation. There is no mixing of the gas in the bed and the gas recirculating inside the bubble. So this happens in the fast bubble regime. So option B is the right answer. When fast bubbles move across the cloud. So that is question 5. Now let us see question 6. In question 6 it is asked that the pressure distribution around a bubble is dash. So now we are talking about pressure distribution. So when we are talking about pressure distribution, what are the three things should come into our mind? The bubble the pressure is constant throughout the bubble. Pressure in the lower part of the bubble is lower than the surroundings, whereas at the upper part of the bubble it is higher than the surroundings. And gas flows into the bubble from the base and leaves at the top. Why? Because at the lower portion the pressure is lower, whereas at the higher portion the pressure is high. So this is the pressure distribution. So now let us see what are the options given and choose right one accordingly. Option A, lower than the surrounding bed. Option B, lower in upper parts. Option C, higher in lower parts. Option D, all of these. So the pressure inside the bed is lower than the surroundings. Option A is the right answer. Pressure in the lower part of the bed is lower than the surroundings, whereas in the upper part it is higher. Thus the gas flows into the bubble from below and leaves at the top. So that is what even I have been saying. So now let us go to, before going to question 7, just give me a minute. I'll just insert page number on these slides, which is missing actually. Slide number, apply to all. Yeah. So now let us see question 7. In question 7, what is asked? In small particulate beds, the wake angle dash. Option A increases. Option B decreases. Option C constant. Option D none of these. What happens in smaller particulate beds? When we are using smaller particles, The bubble formations are flatter in smaller particle beds, and therefore because these bubbles are smaller, the wake angle also reduces. Wake angle decreases with smaller particles because bubbles are flatter in small particle beds. Option B is the right answer. Wake angle decreases with smaller particles. Bubbles are flatter in small particle beds. That is what I have been saying. And that is question 7. And let us go to question 8. In question 8, it is given that gas is distributed across the plate with a bed diameter of 0.5 meter in a bubbling fluidized bed at a minimum fluidization velocity of 1.62 meter per second. It is observed that the mean bed bubble diameter was 4 mm. Calculate the single bubble rise velocity. Option A 10.32 centimeter per second. Option B 8.312 centimeter per second. Option C 14.08 centimeter per second. Option D 13.32 centimeter per second. So what is being asked? It is being mentioned that gas is distributed across the plate with a distributor. We are distributing the gas through a distributor, and the bed diameter is 0.5 meter, and the bed is a bubbling fluidized bed, and the minimum fluidization velocity inside the bed is 1.62 meter per second, and mean bubble diameter was 4 mm, and we are asked to calculate the single bubble rise velocity. So the options are given. Now let us go and find out the proper way to calculate the answer. So out of the options given, answer is option C, 14.08 centimeter per second. So first, what are we supposed to do? First we'll see what is the conditions given in the problem statement. So first one is given. So in that it was mentioned about the bed diameter being 0.5 meter. So that is we have written, and minimum fluidization velocity value was given. It is 1.62 meter per second, and mean bubble diameter value is given. It is 4 mm. So before proceeding, we need to calculate the ratio of dB by dbed. So dB is the bubble diameter, and it is 4 mm, and the bed is 0.5 meter. So here we are calculating it, and we are getting the value as 0.008. So it is less than 0.125. So it is like less than 12.5%. So now the criteria is verified for us to go proceed with using a certain formula. So we have to find the single bubble rise velocity, and the formula is UBR is equal to 0.711 into square root of GdB. So why are we picking up this formula? Because when dB by dbed, that is the diameter of bubble by diameter of bed, is less than 0.125, we can use this particular formula. UBR is equal to 0.711 into square root of GdB. So in this, UBR is the bubble rise velocity, G is the acceleration due to gravity, and dB is the bubble diameter. So this particular formula should be used in centimeter per second. So be careful while you are using the formula and be consistent throughout. So UBR calculation we are doing, UBR is equal to 0.711 into G into dB. So dB is 4 mm. So in centimeter it is 0.4 centimeter, and G is 9.81 meter per second square, and since we are using in centimeter per second square, it is 981. So 0.711 into 981 into 0.4, square root of 981 into 0.4. So what we are getting, it is 14.08 centimeter per second. So please be careful of the units you use, and these are empirical relations. So unit consistency is very important, because you should be using the same unit throughout the problem, and you should also be using the unit given according to the formula. For example, this particular formula works the best in the centimeter per second, the CGS unit. So similar things you should be very cautious while using the formula. So for now, I hope you are clear. I'll give you guys a minute time. So please check and let me know if there are any doubts. So I guess you are clear with that. Now let us go to question 9. Um, in question 9, it is mentioned that upward flow of gas into and out of the bubble for two-dimensional bed is dash, where V, U, F, epsilon, MF, RB and L are gas velocity and minimum fluidization velocity, minimum void fraction RB is should be UMF. So coming back to the question, the upward flow of gas into and out of the bed for two-dimensional bed is the upward flow of gas into and out of the bubble for two-dimensional bed is dash, where V, U, F, epsilon, MF, RB and L are gas velocity, fluid velocity, minimum fluidization velocity, radius of sphere and bed thickness respectively. So the upward flow of gas into and out of the bed, out of the bubble, upward flow of gas into and out of the bubble for two-dimensional bed. So there are two formulae for this particular question. One is for two-dimensional bed and the other one is for three-dimensional bed. So this question is concerned regarding two-dimensional bed. So please be cautious in all these aspects, or else you can also remember by seeing the bed thickness, because in two-dimensional bed we are concerned with the bed thickness also, which we are not that concerned when we are using the three-dimensional bed formula. So these small tricks can help you. Coming back to the options, first option A, it is 4 V is equal to 4 into UF into epsilon MF R into RB into L. Option B, V equal to 4 into UF square into epsilon MF into RB into L. Option C, V is equal to 2 into UF into epsilon MF into RB. Option D, 4 into UF into epsilon MF into RB square into L. So the first thing is, the question is about asking the upward flow of gas into and out of the bubble. So gas flow into and out of the bubble, what is the upward flow velocity? So the question is about two-dimensional bed. So we are asked to find what is the formula we use for finding out the upward flow of gas into and out of the bubble, and that too at a two-dimensional bed. So V is equal to something, and it is a function of UF, epsilon, MF, RB and L. And UF is the fluid velocity and epsilon MF is the minimum fluidization velocity, and RMF is the RB is the bubble rise velocity and L is the bed thickness. So all these formula have something in common. It's a function of all the variables given. So first we have formula, and which we know the answer as 4 into UF into epsilon MF into RB into L. So answer is option A. Option A is the right answer. So just remember that it is a function of 4 different variables, and since it is about gas flow into and out of the bubble, fluid velocity is a function, and actually it is 4 into UMF into RB into L, but we are using UF into epsilon MF because it is like uh, it is an instead of using minimum fluidization velocity, we are using fluid velocity and void fraction at minimum fluidization condition. So that is, so these two terms come together. So if this can be, option B can be ignored on that basis because it is given power in turn the UF place and not in the epsilon MF. So option B we can ignore. And second, it is a function of RB which is given everywhere except in option C. So we are again ignoring option C and we are left with option A and option B. Um, so if you go with unit consistency, you can neglect option D as well. And we'll be left with upward flow of gas into and out of the bubble for the two-dimensional bed then becomes 4 into UF into epsilon MF into RB into L. If we are using the formula for three-dimensional bed, what happens? It happens is that it becomes 3 into UF into epsilon MF into pi into RB square. Instead of L, we have pi RB, and it is becoming 3. The coefficient is becoming 3, and instead of L, it becomes pi into RB if we are using three-dimensional bed. But now the question is about upward flow of gas flow into and out of the bed for two-dimensional bed is dash. So answer is option A, where V is equal to 4 into UF into epsilon MF into RB into L, where V is the upward flow of gas into and out of the bed. I think it is volumetric flow rate, and UF is the fluid velocity, and I mean no, it is gas velocity only, not volumetric flow rate, it is gas velocity. And so dimensional consistency cannot be used, and UF into epsilon MF into RB into L. RB is the radius of bubble and L is the bed thickness. So that's it for question 9. Now we'll go to question 10. In question 10, it is asked that slow bubbles regime is usually for the bed of dash. Option A, small particles and small bubbles. Option B, small particles and larger bubbles. Option D, larger particles and small bubbles. Option C, larger particles and small bubbles. Option D, larger particles and large bubbles. So the question is about slow bubble regime is usually for the bed of dash. I guess it is large particles and small bubbles. Or yeah, we are correct in that aspect. The answer is large particles and small bubbles. So the question is slow bubble regime is usually for the bed of larger particles and small bubbles. So what happens in slow bubble regimes? In slow bubble regimes, emulsion gas rises faster than these bubbles, and hence it is used as bubble as a convenient shortcut. So one thing, if you remember, bubble rise velocity is directly proportional to bubble size. So if you are using if you having small bubble regime, ideally it is smaller bubbles. If you are using slower bubble regime, it is ideally smaller bubbles. So smaller bubbles is the option, and also like smaller bubbles, and we are going for large particles. So option C is the right answer. Now let us go to question 11. In question 11, the type of slugging where gas slug occupies the complete bed cross section is dash. Option A, wall slug. Option B, flat nose slug. And option C, round nose slug. Option D, all of these. So actually, option B, flat nose slug is the answer. So there are three types of slugging. The first one is round nose slug. So where the bubbles would be like this. And I mean, just imagine them at the bed center. This is round nose. And second one is wall slug. Like these bubbles like adhere to the walls of the bed, and this is known as wall. And the last one is flat slugs. So in this, the bubbles will be like this, like they will be occupying the whole region. So when does these things happen? So the round nose slugs or the axial slugs happens with finer size particles when the particles go up and they rain. Where is my cursor? Yeah. And they rain along the walls of the vessels to match the rise rate of these slugs. So this is what we call in round nose or axial slugs. And in wall slugs, the rising slugs adhere to the walls and at a higher gas velocity or angular particles or rough vessels this happens. In flat slugs happens in delta-D particles where the bed is separated into slices of emulsion and emulsion separated by gas. So they rise up bed and it is matched by continuous raining of solids from slice to slice. So here we can see a distinct separation between bubbles and the emulsion phase. So here we can also see the bubble has completely occupied the cross-sectional area of the bed. So answer is flat nose slug. Flat slug is the right answer. Option B is the right answer. I hope you are clear. Now let us go to question 12. In question 12 it is asked that in slugging criteria the wall effect is negligible when dash. So this question I think we have seen n number of times in the last classes. So what is that? In slugging criteria the wall effect is negligible when dash. Option A, bubble diameter is smaller than 0.1. Option B, bubble diameter is larger than 0.2. Less than 1, above 1. The question is little ambiguous, so I'm just adding. So coming back to the question. So in slugging criteria, wall effect is negligible when dash. Option A, bubble diameter is smaller than 0.1 times bed diameter. Option B, bubble diameter is larger than 0.2 times bed diameter. Option C, less than 1. Option D, above 1. So wall effect is negligible when bubble diameter is smaller than zero point 0.1 times bed diameter is the right answer. This particular question we have seen more times. So why it is when bubbles are smaller than certain criteria compared to the bed diameter, we call it wall effect, and we call the wall effects as negligible. So wall effects does not significantly have any effects because the bubble diameter is comparatively smaller than the bed diameter. So option A is the right answer. Now let us go to question 13. In question 13, according to Bayes and Gildat 1974, beyond which bed diameter there is no effect of particle size. So according to Bayes and Geldat 1974, beyond which bed diameter there is no particle effect of particle size. And here d bed is the bed diameter. Option A, d bed is greater than 2. Option B, d bed is less than 1. Option C, d bed greater than 5. Option D, d bed is equal to 1. So in this it is mentioned that beyond a certain bed diameter there is no effect of particle size. So what is that? Like when the bed diameter is significantly larger, there is no effect of particle size. So option C is the right answer. D bed is greater than 5 is the right answer. So this is according to Bayes and Geldat 1974. So beyond which bed diameter there is no effect of particle size. So the right answer is D bed is greater than 5, where D bed is the bed diameter. And that is question 13. Now let us go to question 14. In question 14, it is asked that the time required for the bubble to travel through the bed is expressed as dash, where T is the time required for the bubble to travel through the bed, and H max is the maximum bed height, and UBA is the absolute bubble velocity. So what is asked in this particular question? It is asked how much time is required for the bubble to travel through the bed, and it is expressed as dash. So option A, it is T is equal to H max by UBA, and option B, it is T is equal to 2 times of H max by UBA. Option C, it is T is equal to H max by 4 times of UBA, and option D, it is T is equal to H max by 5 times of UBA. I think B. Yeah. So answer is T is equal to H max by UBA. That is H max is the maximum bed height and UBA is the time required for the bubble to travel throughout the, T is the time required for the bubble to travel through the bed, and H max is the maximum height or bed height, and UBA is the absolute velocity. So I think this is what is right, because what is asked in the question, in this question it is asked that time required for the bubble to travel through the bed. So what is the time required? It is the distance by the velocity. So distance is nothing but the maximum bubble bed height, the maximum height to which the bed can expand. So maximum bed height is H max, and it should be divided by the bubble velocity. So it is divided by UBA, where UBA is the absolute bubble velocity. So this is a straightforward question actually. What is the time required for the bubble to travel through the bed? So for example, we may be asking A is traveling from point 1 to 2 at this particular velocity. So the distance is this. How much time would A take to reach point 2? So similar question is what is asked. The time required for the bubble to travel through the bed is expressed as dash, where H max is the maximum bed height and UBA is the absolute bubble velocity. So we are dividing by the distance traveled by the velocity, and we are getting the answer. T is equal to H max by UBA. UBA. So answer is option A. So now let us go to question 15. Uh, Let us take a 5 minutes break actually. Like time now is 4:01. We'll be back by 4:05. Thank you. So we'll start now. I hope I am audible. Yeah. So an effective way to decrease the slugging and to reduce the maximum slugging bed height is carried out by dash. Decreasing the cross-sectional area towards the top of the fluidized bed. Increasing the cross-sectional area towards the top of fluidized bed. Keep constant cross-sectional area towards the top or bottom of the fluidized bed. All of these. Answer is option B. Sorry. I mean, what I mean to say is the design would be such a way that bottom is constant and at the top it would be increasing. The cross sectional area towards the top of the bed would be increasing, and there is some formula for it which you can find in the lecture notes. But the point to be noted over here is that an effective way to decrease the slugging and increase and reduce the maximum slugging bed height is by increasing the cross sectional area towards the top of the column. So option B is the right answer. Question 16, it is about the product of the decay coefficient is inversely proportional to dash. Option A, liquid velocity and density. Option B, gas velocity. Option C, viscosity of liquid. Option D, surface tension of liquid. Option B is the answer. Yeah. Product of decay coefficient is inversely proportional to gas velocity. So option B is the right answer. Now let us go to question 17. In question 17 it is given that following assumptions are true for Cooney-Eleven spill. Option A, gas stream will completely dispersed solids. Gas stream with completely dispersed solids. Option B, agglomerates coming from the bed. Option C, agglomerates and thin wall layers of particle moving downwards. All of these is the right answer. Because if you remember in Cooney-Eleven spills model, assumption is that there are three phases they will be assuming. One is the gas phase with completely dispersed solids, and second is the agglomerate coming from the bed and moving towards the top, and third is agglomerate and thin layer of particles moving downward. So all three is considered for Cooney-Eleven spills model. So answer to this particular question is all of these. So I hope you are clear. Moving to question 18, it is given that in a slugging, where is my cursor? In a slugging fluidized bed regime, the influence of wall is negligible when dash. D bed is the bed diameter. Option A, D bed less than 0.2, and option B, D bed greater than 0.3. Option C, D bed greater than 0.2. Option D, D bed less than 0.1. Option D is the right answer. D bed is less than 0.1. This question we have seen in last few slides before as well. So I am just skipping to the next question. Okay, this question is not the same. It is about the bed diameter. When bed diameter is smaller, um, it is influence of wall is negligible. Just check with this question. Now going to question 19. In question 19, the zone where bulk density decreases with bed height is dash. Option A splash zone, option B lean zone, option C dense zone, option D all of these. So in fluidized bed actually we have two different zones where the density, the solids are almost present, and the top zone where density of solid decreases with bed height. So the top zone is known as lean zone and bottom zone is known as dense zone, and the region in between the both zones is known as splash zone. So in this particular question, it is clearly asked that the zone where bulk density decreases with bed height. So it is mainly concerned with the zone where the bulk density is decreasing with the bed height. So in dense zone, there is no decrease of bulk density. So my option C is not the answer, whereas option A, it is the zone between dense zone and lean zone. So we cannot clearly distinguish that. Whereas the option B, that is lean zone, is a zone where bulk density decreases with bed height. So that is why we say in entrainment and elutriation that the solids are carried to the top with increase in fluid velocity. So imagine there are some solids being carried, but not all the solids are being carried. So generally the bulk density is getting reduced with the bed height. That is why in lean zone it is bulk density decreases with bed height. There is a zone above lean zone known as transport disengaging height, where the bulk density remains constant with bed height. So general design is to go as such height, but for this particular question, the zone where the bulk density decreases with bed height is known as lean zone. Option B is the right answer. So this is part is coming under entrainment characteristics in the fluidized bed. And lastly, we are going to question 20. In question 20, the entrainment is significantly influenced by dash. Option A, high gas velocity. Option B, low gas velocity. Option C, density and viscosity. Option D, all of these. All of these is the answer, I guess. Yeah, all of these, because like entrainment characteristics is influenced by the velocity of the fluidized bed and velocity of the fluid medium, density and viscosity of the medium as well. And of the fluid as well. So because all these things play an important role in determining which is the entrainment zone, and whether the particles can be carried over or not is like depending on all the fluid properties and the particle properties as well. So all of these is the right answer. Now let us go to I think these are the problems associated till week, I mean associated from week 8 problems, which will be helping you guys in solving the assignment for this particular week, and you can submit it on time. I think Wednesday is the deadline. Make sure and submit the assignment, because these assignments also carry some weightage in the final marks which you will be getting. So that's it. Now let us go to the next section, that is week 7 assignment problem. So just to discuss the answer and have some discussion, because we have time, that is one thing. And also like these are some different problems, we can have some different perspective in dealing with these problems as well. So that is why we are dealing with assignment from questions from week 7. So if you have any doubts from last week's problem also, you can ask me now. So we'll start with the problems. So question 1, it is about what is the unit of turbulent dissipation rate? E. So now the question is about turbulent dissipation rate E, and options are option A meter square per second, option B meter cube per second, option C meter square per second square, option D meter square by second cube, Option D is the answer. That is unit of turbulent dissipation rate is meter square per second cube. Why? Turbulent dissipation rate epsilon is the rate at which turbulence kinetic energy is converted into thermal internal energy. So it is the unit converter, rate at which unit is getting converted. So it is joules per kg per second. So it is, if you write it as joules is Newton meter and Newton meter is joules, Newton is kg by meters, kg into meter per second square and into meter. So kg meter square per second square. So kg meter square per second square divided by kg second, and it becomes kg gets cancelled and meter square remains, and seconds into second square becomes seconds cube. So option D is the right answer. Option D. Now let us go to question 2. In question 2, the most important force in stabilizing the bubble is dash force. Option A, viscous force. Option B, surface tension force. Option C, inertial force. Option D, none of the above. Option B, surface tension force is the right answer, because in order for the bubble to be stable, the question is about stability of the bubble. So hence surface tension is the important force in stabilizing the bubble. Option answer is option B. I hope it is clear now. We'll go to question 3. Okay, question 2, we have some results show that surface tension of air liquid interface exerts a huge impact on bubble stability by reducing the surface free energy and increasing Gibbs surface elasticity. However, surface tension may not be the only determinant of bubble stability. So this line is taken from this particular reference, a review on bubble stability in fresh concrete mechanisms and main factors. So it shows that surface tension of the air liquid interface, that is the bubble interface, exerts a huge impact on bubble stability by reducing the surface free energy and increasing the Gibbs surface elasticity. So what it is doing, surface tension is having a huge impact on bubble stability. What it is doing, it is reducing the surface free energy and increasing the Gibbs surface elasticity so that the bubble remains stable. But surface tension is not the only one determinant of bubble stability. So that is also an important point to be considered over here. Although it is not it is not the only factor. It is an it is an important factor, or it is a significant factor. What is a significant factor? Surface tension is a significant factor in it is an significant factor in the, like, in terms of the bubbles maintaining the stability. So that is question 2. And in question 3, if the bubbles are much larger than the micro scale of turbulence, choose a force which can be neglected. Option A, viscous force. Option B, surface tension force. Option C, inertial force. Option D, none of the above. So here what we are saying, the bubbles are larger than the microscale of turbulence. So which force can we neglect? So answer is viscous force is the answer, because it's because, like, imagine the bubbles are larger than the turbulence microscale. So at that condition, like, we can say that viscous force is not playing an any impact over there. Like, these bubbles are larger than the turbulence scale itself, so viscous force is not having any significant impact, so we can neglect that. Option A is the answer. Now let us go to question 4. In question 4, it is asked that the centrifugal force can disintegrate the bubble as it increases with an increase in bubble size. The bubble breaks up when centrifugal force is dash. This surface tension force, especially at high pressures when gas density is high. So what is asked? Centrifugal force increases with increase in bubble size. So when centrifugal force is higher, it can disintegrate the bubble, it can break the bubble. So, say bubble, that is the first statement. Second statement, it is asking that bubble breaks up when centrifugal force is dash than the surface tension force at higher pressures when gas density is high. When centrifugal force is greater than surface tension force, the bubble breaks up. Option A less than, option B more than, option C equal to, option D none of the above. So answer is option B, more than, because in the first statement itself it is clearly mentioned that centrifugal force can disintegrate the bubbles. When there is an increase in bubble size, the centrifugal force increases. So when centrifugal force increases, the bubble is disintegrating. So when centrifugal force is greater than the surface tension force at a higher pressure and gas density high, the bubbles breakup occur. So option B, more than, is the right answer. So now let us go to question 5. In question 5 it is mentioned that according to Ojima et al. 2015 model, what will be the coalescence time in the slurry fluidized bed? Option A, coalescence time is independent of slurry concentration. Option B, coalescence time increases as slurry concentration increases. Option C, coalescence time decreases as slurry concentration increases. Option D, none of the above. So in this particular question is about Ojima et al. 2015 model, and it is relating the coalescence time and the slurry concentration inside the fluidized bed. So imagine that you have a slurry of particles. You have 5% solids and 20% solids, in which the coalescence coalescence time is nothing but the time the particles spend with each other for them. I mean the bubbles spend with each other for them to collide, for them to coalesce and grow in size. So when the coalescence time can be higher, when the slurry concentration is more, the probability of those bubbles coming in contact is high. So therefore we can say that coalescence time decreases. Because the concentration has increased, the probability of them coming together or is increased. So therefore the coalescence time is also decreasing. Like the coalescence time is decreasing when slurry concentration is increased. Like if you are not sure of the answer, think logically and answer. Most of the time it will be like correct if your understanding of the concepts is better. So what we are saying is that coalescence time has decreased as the slurry concentration increases. Because in the slurry fluidized bed, if the concentration is increased, the chances of the bubbles coming together is also enhanced, and therefore the coalescence time is decreased. So option C is the right answer. The time Tc elapsed from the bubble contact to the rupture of the liquid film between two bubbles in a quasi two-dimensional column was measured to investigate the effects of particle diameter on coalescence. Tc decreases, in other words, bubble coalescence is enhanced with decreasing particle diameter, which results in the reduction of gas holdup of the slurry bubble column. The interaction between the bubble interface and particles in the bubble coalescence process after bubble contact is a local phenomena and rarely depends on the macroscopic behavior of the interface. Coalescence time decreases as the slurry concentration increases or the particle diameter increases. So here it is clearly explained that Tc, that is the coalescence time, is nothing but time elapsed from the bubble contact to the rupture of the film between those two bubbles, or in other words, it when you are increasing the slurry concentration, the bubble contact, the time from the bubble contact to the rupture of the liquid film decreases, or bubble coalescence is enhanced with increase in the slurry concentration or decrease in the particle diameter. The question can be asked in any way. Coalescence time decreases with increase in the slurry concentration. Coalescence time decreases with decrease in the particle size. The particle diameter decreases, coalescence time decreases. Coalescence time decreases, slurry concentration is increased. Coalescence time decreasing का मतलब, that is the coalescence time decreases, coalescence is enhanced. Coalescence, bubble coalescence phenomena is enhanced with coalescence time decrease. I hope you are clear now. just look at the slide, you will be more clear than me speaking, because I may be confusing, but just look at it once. So now it is question 6. In question 6, it is given that centrifugal force induced by dash circulation of gas in a bubble. Option A internal, option B external, option C due to both internal and external, option D none of the above. So centrifugal force is induced by the internal circulation of gas in a bubble. Option A is the answer, because centrifugal force, it is like pushing the bubble boundary, we can say. So why is that happening? Because of the internal circulation of gas happening inside the bubble. So because of the internal circulation of the gas happening inside the bubble, the centrifugal force is induced. So do you remember what we discussed about centrifugal force and bubble disintegration? Centrifugal force increases, bubble disintegration happens. So how this centrifugal force is produced or induced? It is caused by the internal circulation of gas in a bubble. So when you are studying some concepts, always relate to the previously studied concept, so it can stay in your mind for a longer period. So that is question 6. In question 7, in the bubble coalescence model, choose the correct option. Option A, collision of 3 or more bubbles at the same time has a very limited probability, very small probability. Option B, binary collision is normally considered. Option D, both options A and B are right. Option D, only option A is correct. So this question we have discussed in a different sense in the last week. So it is nothing but bubble coalescence model. When we are considering that, what is the correct option to consider? Option A, it is collision of 3 or more bubbles at the same time has a small probability. This question we have discussed in last class actually. When we are talking about bubble coalescence, at the same time more than two bubbles cannot collide, or in other words, the collision of more than three bubbles, three or more than two bubbles, three or more bubbles has a very small probability. So on that assumption basis, mostly we'll be considering only binary collisions. So these coalescence models are based on the consideration of two bubble collision at the same time. So the at the same time is the keyword over here. At the same time, collision of three or more bubbles has a very small probability, and also the binary collision is only considered normally. So now it is clear, I guess. So option C is the right answer. Both options A and B are correct. So in the bubble coalescence model, the correct option is that collision of three or more bubbles at the same time has a very small probability, and bubble collision is normally considered. Sorry, binary collision is normally considered. Binary meaning two. So two or more bubbles not two or more, two bubbles colliding at the same instant is considered, but three or more bubbles collision at the same time has a very small probability, so that is not normally considered. So only we are considering binary collisions, that is two bubbles colliding. So both options are right, so answer C, option C is the right answer. So question 7 we have seen. Now let us go to question 8. In question 8, coalescence of two bubbles in a turbulent flow in three-phase fluidized bed is usually considered to occur in 3 steps. Choose the correct sequence. Option A, surface of colliding bubble flattens against each other. Option B, trapping a small amount of liquid between colliding bubbles. Option C, bubbles collide. So we are asked to find the correct sequence when two bubbles are colliding and coalescence is occurring. So we ourselves can look at it before looking at the options also. So there are 3 steps given. The first one is surface of colliding bubbles flatten against each other. Second one, trapping a small amount of liquid between colliding bubbles, and the third one, bubbles collide. So what happens in the coalescence of two bubbles? First, what should occur? First, the bubbles should come and collide with each other. So third statement is the first statement. Two bubbles collide. The bubbles collide. Second statement, what happens when these bubbles collide? When these bubbles collide, the surface of the first step, it is like bubbles coming against each other and they are colliding, right? Bubbles colliding. And when they collide, the surface of the colliding bubble flattens against each other. So this is first, this is second, and they trap a small amount of liquid between colliding bubbles. So this one is the third statement, and after that this becomes ruptures and we get a larger size bubbles. So that is what happens. But coming back to the question, the surface of bubbles, coalescence of two bubbles in a turbulent flow in a three-phase fluidized bed is usually considered to occur in 3 steps. First one, the bubbles collide. Second one, surface of the colliding bubble flatten against each other. Third one, trapping a small amount of liquid between colliding bubbles. And lastly, the surface ruptures and we get a larger bubble. So now let us look at the option. Option A 1, 2 and 3. Option B 2, 1 and 3. Option C 3, 1 and 2. Option D none of the above. So what is the answer? Option 3, 1 and 2 is the right answer. So according to us 3, 1 and 2. So answer is option C is the right answer. Option C is the right answer. So I hope you are clear now. Now let us go to question 9. According to Prince and Blanche 1990, the collision frequency model is defined as dash. Option A, given theta ij is the collision frequency, theta ijt is the turbulent collision rate, theta ijb is the buoyancy driven collision rate, theta ijls is the laminar shear collision rate. So, option A, theta ij is equal to theta ijt plus theta ijb. Option B, theta ij is equal to theta ijt plus theta ijb plus theta ijls. So option C, theta ij is equal to theta ijb plus theta ijls. Option D, theta ij is equal to theta ijt plus theta ijls. So according to Prince and Blanche 1990, the collision frequency model is defined as dash, and the collision frequency is equal to turbulent collision rate, buoyancy driven collision rate and laminar shear collision rate is the right answer. So the collision frequency is model is defined according to Prince and Blanche 1990 model as the sum of all the collision rates. So the first one is turbulent collision rate, And second is buoyancy driven collision rate. Third one is laminar shear collision rate. So option B is the right answer. Option B, theta ij is equal to theta ijt plus theta ijb plus theta ijls. So answer is option B. Now let us go to question. Okay, question 9 answer. Bubble coalescence is modeled by considering bubble collisions due to turbulence, buoyancy and laminar shear, and by analysis of the collision efficiency of coalescence efficiency of collisions. Bubble breakup is analyzed in terms of bubble interaction with turbulent eddies. So this is Prince and Blanche 1990 model, and I have given you the DOI also. You can go and check their papers also if you are very much interested. Now let us go to, what they are saying is bubble coalescence is modeled by considering three phenomena: bubble collision due to turbulence, bubble collision due to buoyancy, bubble collision due to laminar shear. And by analysis of the collision efficiency of these collisions, we are modeling the bubble coalescence. Coalescence efficiency of these collisions, we are modeling the bubble coalescence. And second statement, it is bubble breakup is analyzed in terms of bubble interaction with turbulent eddies. This is extra information, you need not worry about that. We have 10 more slides, but we have plenty of time actually, so we can go with that leisurely also. We have 37 now. It is 20 more minutes we have and 10 more problems. I think we can cover it very quickly also. Okay, question 10, it is about the maximum stable bubble size as per Leo et al 1999 model is expressed as dash. Option A, D max is approximately 2.53 times sigma by rho g into g. Option D, it is D max is approximately equal to 2.53 into sigma by rho g g power 2 by 3. Option C, it is D max is approximately equal to sigma by rho g g. Option D, D max is approximately equal to 2.53 into sigma divided by rho g g to the power of 0.5. So maximum stable size as per Leo et al 1999 model is expressed as dash. So answer I guess is D. Yeah, answer is option D, that is D max is approximately equal to 2.53 into sigma by rho g into g to the whole power of 0.5. So how we are getting this particular formula? This particular formula is obtained from Leo et al 1999 model. For the model is for getting the maximum stable bubble size. So here we are relating sigma surface tension divided by density of gas and gravitational constant. So it is 2.53 into sigma divided by rho g g to the whole power of 0.5. Option D is the right answer. Now let us go to question 11. In 11 it is given as per Quilaglo and Tavlerites 1977, which of the following is the correct expression for liquid droplet coalescence rate? So as per Quilaglo and Tavlerites 1977 model, which of the following is the correct expression for liquid droplet coalescence? So option A, it is Tc is equal to exponential of minus Tc by Ti. And second, option B, it is Pc is equal to exponential of Tc by Ti. Option C, Pc is equal to exponential of minus Tc by 2 Ti. Option D, none of the above. This question also we have discussed in the last class itself. Pc is the coalescence probability, and Tc is the coalescence time, and Ti is the interaction time. So Pc equal to exponential of minus Tc by Ti is the right answer. Option A is the right answer. How? As per Coelaglo and Tavlerites 1977, breakup is caused by collisions of drops with turbulent eddies. Okay. First statement, it was about bubble breakup, so I just removed that. Coalescence rate can be expressed as a product of collision frequency and coalescence efficiency, since not all collisions between droplets leads to coalescence event. So not all the collisions between the two droplets lead to coalescence. So how coalescence rate is expressed? Coalescence rate is expressed as a product of collision frequency and the coalescence efficiency. So this is an important statement. Second one, for coalescence of droplets to occur in a turbulent flow field, droplets must first collide and then remain in contact for a sufficient time. See, we are saying that not all collision leads to coalescence. So when does coalescence occur when two bubbles collide? When they remain in contact for a sufficient period of time, so that the processes of film damage, that is we have seen, right, two bubbles collide and they remain in contact and the surface between them align against each other and they trap some liquid and then they break up. So that processes of film drainage, film rupture and coalescence may occur. So these bubbles or these droplets should remain in sufficient contact against each other, should remain in contact for a sufficient period of time. During these processes, a turbulent eddy may separate the droplets and prevent coalescence. Sometimes these turbulent eddy may separate the droplets and they may prevent coalescence also. The force which compensates the drops must act for a sufficient time that the intervening film drains to a critical thickness, so the film rupture and coalescence will take place. It becomes obvious that the time for these processes to occur, the contact time must exceed the coalescence time of the droplets. What we are saying, the interaction time, where the two droplets remaining in contact, that particular time, that is the interaction time Ti, should be greater than the coalescence time Tc. For example, if it is taking 5 seconds for the coalescence to occur, like let us say in 5 seconds the coalescence will be successful. For the two bubbles to be successfully coalesced, it should be remaining in contact for time period of more than 5 seconds or at least equal to 5 seconds. So that is what is given over here, and it is given by Pc is equal to exponential of minus Tc by Ti according to Coelagro and Talright's 1977 model. So that is question 11. Now let us go to question 12. The unit of collision frequency between bubbles with a diameter of di and dj is defined as dash. Option A, meter square per second square. Option B, meter cube per second cube. Option C, 1 by meter cube second. Option D, meter square per second cube. Answer is 1 by meter cube second is the right answer. Option C is the right answer. Unit of collision frequency between bubbles with diameters di and dj is defined as, it is collision frequency, right? So it is obviously 1 by second and it is 1 by meter cube second. So since it is with two bubbles with two diameters di and dj, 1 by meter cube second. So question 13, and it is the what is that, turbulent dissipation rate, meter square per second cube, which we saw in question 1. It is square per second cube, and 1 by meter cube second, that is 1 by meter cube second, is the bubble collision frequency between two bubbles di and dj in diameter. Collision frequency 1 by meter cube second. I hope it is clear. Now let us go to question 13. In question 13, it is given that for the slurry column, which statement is correct? Option A, bubble coalescence enhanced with decreasing particle diameter. Option B, bubble coalescence reduces with decreasing particle diameter. Option C, bubble coalescence is independent of particle diameter. Option D, none of the above. So for the slurry column, which statement is right? The bubble coalescence is enhanced with decreasing particle diameter. So we have seen in the last few slides before itself how coalescence is enhanced. That is, the coalescence time is decreased with increase in slurry concentration or decrease in particle size. If coalescence time is reduced, bubble coalescence is enhanced on the other words. So option A is the right answer. Bubble coalescence enhanced with decreasing particle diameter, because the same statement, time Tc elapsed from bubble contact to rupture of liquid film between two bubbles in a quasi-static, quasi-two-dimensional column was measured to investigate the effects of particle diameter on bubble coalescence. Tc decreases, in other words, bubble coalescence is enhanced with decreasing particle diameter, which results in reduction of gas holdup of the slurry column. The interaction between bubble interfaces and particles in the bubble coalescence process after bubble contact is a local phenomenon and rarely depends on the macroscopic behavior of the interface. Coalescence time decreases as the slurry concentration increases or the particle diameter decreases. So, coalescence time decreases with decrease in particle diameter and increase in slurry concentration, and coalescence is enhanced with decrease in particle diameter and increase in slurry concentration. So that is question 13. Now we'll go to question 14. Which of the following statement is true? Option A. Bubbles of different sizes have different rise velocities. Option B. Bubbles of different sizes have same rise velocities. Option C. As per Prince and Blanche 1990, collision model is a summation of turbulent collision, buoyancy driven collision and laminar shear collision rate. Option D. Both option A and C are correct. So the third statement we have seen only now, that is, as per Prince and Blanche 1990 model, collision model is a summation of turbulent collision rate, buoyancy driven collision rate and laminar shear collision rate. So all three are true. So we know option C is the right answer. And coming back to options A and B, option A, it is given that bubbles of different sizes have different rise velocities, and in option B it is a contradictory statement of bubbles of different sizes have same rise velocity. So we all know that bubbles rise velocity is different for different sizes, and we also know that how it is proportional to the size of the particles, that is bubble rise velocity is proportional to the size of the particles. If it is a smaller size particles, bubble rise velocity is lower compared to the larger size particles whose bubble rise velocity is higher. So first statement is right. Bubbles of different sizes have different rise velocity. True. Second statement is false because different sizes have different rise velocities, not the same. So it is option B, it is false. Option B, it is false. Option A, it is true. And option C, again it is true because collision model is a summation of turbulent collision rate, buoyancy driven collision rate and laminar shear collision rate. So A and C are right. So correct answer to this particular problem is option D. Both options A and C are correct. I hope it is clear. Now let us go to question 15. According to Lee et al. 1987 bubble breakup model, choose the correct option. Option A. Only eddies which have length scale comparable to the bubble diameter can cause breakup. Option B. Eddies of a larger scale will give the bubble a translational velocity. Option C. Both A and B are right. Option D. None of the above. So option 1, A, it is given that only eddies which have a length scale comparable to the bubble diameter can cause breakup. This is true. In other cases, there would not be any significant impact. So eddies which have a length scale comparable to the bubble diameter will lead to breakup. Other cases it won't. And eddies of a larger scale will give the bubble a translational velocity. So both the statements are true. Therefore, the answer is option C. Both options A and B are correct. Let us go to question 16. In question 16, the wall effect predominates when equivalent bubble diameter is dash more than 1/3 of bed diameter, more than 1/6 of the bed diameter, less than 1/3 of the bed diameter, none of the above. So in this particular question, it is about when bubble diameter is when wall effects are predominant, and that is that when is a comparison between bubble diameter and bed diameter. So we can say that wall effect is predominant when equivalent bubble diameter is greater than one third of the bed diameter. If it is larger than one third or 30% of the bed diameter, one third of the bed diameter, the wall effect are coming into picture, because now the bubble size is larger compared to the bed diameter. So option A, more than one third of the bed diameter, is the right answer. This question also we have seen clearly in the last classes and previous classes itself. So by now we are very much clear in this concept and we have a good understanding, I hope. So answer is option A, more than one third of the bed diameter. Now let us go to question 17. In case of aggregate fluidization, the bed appears to be divided into bubble phase. Option B, emulsion phase. Option C, both A and B. Option D, none of the above. So we know that in case of aggregate fluidization, the bed is appearing to be divided into emulsion phase as well as the bubble phase. So both options A and B are right. Option C is their right answer, therefore. Now let us go to question 18. Hydraulic diameter of the bed D bed E is expressed as dash. Option A, 2 into cross-sectional area available to the fluidized bed divided by total wetted perimeter of the bed. Option B, 4 into cross-sectional area available to the bed divided by total wetted perimeter of the bed. Option C, 2 into total wetted perimeter of the bed divided by cross-sectional area available to the fluidized bed. Option D, 4 into total wetted perimeter of the bed divided by cross-sectional area available to the bed. So when does hydraulic diameter comes into picture? When the bed has several internals, we need some equivalent bed diameter to be used. So how it is calculated? It is similar to the hydraulic diameter calculation. So it is 4 into cross-sectional area available to the bed divided by total wetted perimeter of the bed. Option B is the right answer. First thing, here we can easily rule out two options. That is, last two options can be easily ruled out, because if you see unit wise, it is perimeter divided by cross sectional area. So perimeter is unit of meters and it is divided by meter square. So the units we are getting is 1 by meter. So in that, on that basis we can rule out option C and D. But option A and B we need to know the coefficient. So it is 4 into cross sectional area available to the bed divided by total wetted perimeter of the bed. So answer to this particular question is option B is the right answer. 4 into cross sectional area available to the fluidized bed divided by total wetted perimeter of the bed. So that is the formula to calculate the hydraulic diameter of the bed. So when do we use this? We use this when there are several internals available inside the fluidized bed. Internals like heat transfer. For heat transfer we can place some internal rods, something. So in those cases we need hydraulic diameter of the bed for calculation purpose, and therefore we use this particular formula of 4 into cross sectional area available to the fluidized bed divided by total wetted perimeter of the bed. So I think this is the last question for today's session. I thank you guys very much for attending the session, and if you have any doubts, please let me know. We can discuss now. These sessions are being recorded and will be available to you, and you can view these sessions anytime, and if there are any doubts you can give it to me through NPTEL or what do you call, like interaction, that Google Groups is there where you can post your questions, I can answer them. And apart from that you can also like ask me anytime. If you have any doubts, I'll be happy to answer those questions also. And if I'll just wait for 5 minutes. If you have any doubts, please let me know from today's sessions or previous sessions also. You can ask doubt. And that's it from my end. Like, please submit your assignments on time. They also have certain weightage in the final score you get. So if you are uh, sincerely aiming to write the exam, please make sure that you are doing these things on time. So that is from my end. Now, if you have any doubts, please let me know, or I can wait for 2-3 minutes and we can discuss. Yeah, thank you. So, since no one is actually in the call now, I mean, I think they left at the call end. I'll close the session, and if there are any doubts, as I mentioned, there are Google groups from the NPTEL end, so in which you can post your doubts related to assignment problems or my sessions. I'll give you the answers there, and if not, you can ask me in the next class also, uh, which I'll be again happy to take also. So that's it from my end. Thank you everyone. We'll meet again on next Saturday at the same time. um, Thank you everyone.